Good morning to everyone, or good afternoon, I think, depending on where you are. So it's good morning for me. And I'm really excited, to tell you about some of our recent work that we've been doing here in my group and also as a collaborative project. And as you heard, the title is AI-guided closed-loop discovery of photostable light harvesting molecules. So I wanted to begin with some acknowledgements. You'll see as I move forward, this has been a highly collaborative project. There's been 4 PIs and over 8 graduate students, and it's taken us over 3 years to get to the point where we can share these results with you, and we have a finalized story. So you'll see also as I move forward, there's essentially 3 sub-teams that have contributed to this research. The synthesis sub-team led by me, and then also by my colleague in chemistry here at Illinois, Marty Burke. The AI sub-team led by my colleague Nick Jackson in chemistry, and also the characterization sub-team led by Ying Diao, another colleague I have here who's in the Beckman Institute. And the funding for this project came from the National Science Foundation. So this is an NSF AI institute called the Molecule Maker Lab Institute that we have here at Illinois. So I wanted to begin with an imagine if statement. Okay, so imagine if we could design and make nearly any molecule or oligomer that we wanted with desired functionality, right? But using modular synthesis, so using building block based synthesis. And that's really the key for envisioning what I'm trying to show here. This, then makes you think a little bit about, a molecular industrial revolution, right? So imagine we could use modular synthesis to make functional molecules, let's say for organic laser dyes, right? So I'm showing a phenylene vinylene type molecule there. Imagine you wanted to make analytes, so new reagents for redox flow batteries, right? So there's a benzotriazole shown there. Imagine you wanted to make new building block units or new functional molecules for organic light harvesting molecules. And that's actually what I'm going to talk about today. And there's a benzodithiaphene donor and a thiophene acceptor kind of shown in that polymer repeat unit there. But we can also think about natural products. I'm not going to talk about that today as well, but here's a carotenoid structure, which could also be used really for light harvesting as well. And so the key takeaway then, I think, for today's talk is, this talk will convey the significance of combining modular building block synthesis with AI and machine learning, right, to guide the discovery of new functional materials, right? So the emphasis really is on achieving function, not necessarily a structure. So the motivation for our work, really stems from the fact that, in recent years, AI-guided closed-loop experiments have provided a nice, promising method to optimize objective functions. So if you have some experimental campaign and you're trying to optimize some experimental quantity or property, this is a really nice way to do it. There's a lot of different examples I can give you from the literature. So the one on the left here is an example where people were using automated screening of processing conditions for organic solar cells. Okay, so they were changing things like annealing time and also dopant concentration to maximize hole mobility, right? So this was interesting. It was a self-driving lab, but there was no automated synthesis involved. And on the right is another example, but this is more for chemical synthesis. They were optimizing, a chemical reaction, but in batch. Okay, this is work from Jason Hines' group. They were optimizing stereoselective synthesis, or basically for CC bond coupling. And a lot of other additional examples I can give you, right? This is a very active area of research at the moment, everything ranging from, design of pi conjugated peptides, right, to achieve different self-assembly or electronic properties, all the way to solid state materials, right, MOFs, right, for catalysis. And you can see a lot of names you probably recognize, a lot of active work in this area. But I would argue, right, that we have to go beyond just sort of computational predictions of possible or putative chemical structures. Right. In other words, if you really want to make, practical progress, I would argue you have to couple in automated synthesis. This is going to be required to navigate these really large chemical spaces when you, address a very large AI campaign. So, what has been done recently in the area of robotic or automated synthesis, right? There's a couple of examples I'll give you here. I say early examples in quotes because, this is only a couple of years ago. Right, but in 2018 and 2019, some nice work from Lee Cronin's group. He's also in the UK. He was basically demonstrating that you could automate batch synthesis, batch organic synthesis. There's a picture actually from one of his setups there in his fume hood, but he developed some new hardware and software for automated robotic synthesis, also some machine learning for prediction of reaction success. A lot of work coming out of Klaus Jensen's group at MIT, but he's more on the flow-based synthesis side, so not batch, but flow-based synthesis for organic compounds. And this is work from 2019, where they brought in computer-aided synthesis planning. They also brought in some retrosynthetic analysis and modular unit operations. It's actually a nice chemical engineering problem when you start to talk about unit operations. But other recent work, like in the last couple of months, additional work from the Jensen group is now emphasizing not molecular structure, but getting to the point where we can actually target a property, a desired property, right? So again, it's closed loop, AI-guided closed loop synthesis using flow-based synthesis, but optimizing the properties for organic dyes. Okay, so that's interesting. And then also very recently, in the last couple of months, some work from Gabe Gomez's group starting to bring in large language models, right, to guide chemical research. I would say this is a nice first example where large language models were used to guide synthesis planning and to sort of help out experimenters with their projects. And so I think this is all very exciting, right? I would say, though, all of these approaches tend to focus on carrying out general reaction chemistries, right? And so if you go to your organic chemistry textbook, right, there's a lot of different reactions in there, and you think about the challenges in trying to automate a general reaction chemistry, that's, it's a steep sort of ask. So there's some key challenges, I think, to address that in trying to automate sort of all possible or any possible reaction chemistries, right? And so let me just list a couple of challenges, and then I'll tell you how we address this. So the first challenge I kind of already alluded to, right? Organic synthesis, the field of organic synthesis traditionally has been highly specialized, right, for each unique chemical reaction. This really tends to complicate automation when you think about, optimization of reaction yields, for example. In addition, you start to think about bringing in large language models. Language is modular, right, and easily adapted to transformers, the way in which we speak, right? But traditional chemistry, not so much. And there's an example there that I can give you if you're interested, where some researchers looked into this recently. A second challenge is, I've already kind of mentioned this in the introduction. Typically, material scientists, or I would say molecular innovators, want a function. They don't really care so much about the structure, right? But a lot of the work so far has been geared toward targeting particular molecular structures and not really thinking about function as much. The third challenge in developing these really large AI campaigns is that you need data, right? You absolutely need large amounts of data. But from what our experience, and then also my colleagues' experience, is that existing literature may not actually be useful, right, in guiding synthesis planning, right? And the problem really lies in that what's published in the literature is actually just the positive results, right? So you run into this positive reporting trend problem and essentially selection bias, right? If you're trying to use that information to develop optimized reaction conditions, let's say, for example. So what is our approach, right? How do we address this particular challenge, or these sets of challenges, and how can we use automated synthesis in a practical way, right? So our approach, we're not trying to do all possible chemistries using machines, but rather we are using chemistry that machines can efficiently do, right? And there's an important difference there. It's a subtle difference, but it's actually a really important difference in how we sort of address these problems and these AI campaigns, right? So if you think about kind of schematically or graphically how we address this, we adopt modular Lego-like synthesis of these functional materials, right? So to kind of give you a picture, kind of a physical picture of how we may think about this, imagine you go into a Lego store, right, and you're faced with all these different building block units that you can pick and choose, right, and then sort of snap them together and build up a structure. That's exactly what we're doing, except we envision these individual Lego blocks as the individual modular building block units in our chemistries. So we can pick and choose different modular building blocks, snap them together using the same chemical reaction. So we only really have to worry about optimizing one chemical reaction, and then target a functional property or a functional material. So that's exactly what we're doing. And, in fact, right, this has been done before, right? If we think about, the field or the usage of automated synthesis, this really has been revolutionary in the past for large numbers of important molecular classes. Right, you think about polypeptides, right? That has been automated by solid phase synthesis that really enabled the field of proteomics. We think about oligonucleotides, has also been automated, has enabled the field of genomics. And actually oligosaccharide synthesis has also been automated. It's a little less popular, right? But Peter Seeberger's group has worked on this, but nevertheless, it still exists. And furthermore, actually, nature has already figured this out, right? So nature already uses a modular building block approach to make its important, biological polymers. We think about polypeptides. The repeat unit, basic repeat unit is amino acid. Oligonucleotides, right? It's a nucleoside, and of course, again, oligosaccharides. This is a saccharide, beta-D glucose, just showing, one example there. So let me sort of show you then, side by side, and to give you a sense of the chemistry that we use. But let me start, to compare it next to peptide synthesis. I'll start there, maybe more familiar with people who have used solid phase synthesis for peptides. So in peptide synthesis, you want to form amide bonds, right? So you bring in your growing peptide chain. So it's kind of shown on the left. You have your exposed primary amine. Okay, you bring in your next N-protected amino acid. You then couple them together, amine carboxyl coupling, right? And then you add a weak base to just deprotect the next primary amine. And that FMOC is the protecting group, and that goes away. And you can repeat this over and over. Repeated cycles of protection and coupling. So that's exactly what we're doing, except we're doing this for CC bond formation, carbon-carbon bond formation, right? So we have our growing synthetic molecule. We have our exposed boronic acid. We bring in our next B-protected haloboronic acid. Okay, we couple it with Suzuki coupling. And again, add a mild base. And then this protecting group, it's a meta-protecting group, that basically goes away. And we can repeat this process over and over. Repeated cycles of deprotection and coupling. And that's exactly what we're going to do, right, for the work that I'm going to tell you about. Essentially, this is then modular building block synthesis, right? It's automated. It can easily be automated, and it's also iterative. Okay, so we're going through multiple cycles then of just deprotection, couple, purify, deprotect, couple, purify over and over, and we can synthesize these sequence-defined oligomers or organic molecules. We're not quite to the level of polymer yet, right? But we're working on it. That's the current area of interest for us. So, right, you can imagine, because of the modularity here, right, this can be automated. And so there's a picture of an automated synthesis instrument from actually one of my graduate students, former grad student, Eddie Gyra, built that. We call that version 2.0. This is really, all this work is really built on the seminal work and the really, impressive work from my colleague, Marty Burke. And you see the reference at the bottom there, and he had a science paper in 2015, which really just laid this out and showed that it is possible. And we've been, taking this and optimizing it and using it, adapting it for different, materials problems since. So we have now several of these instruments located in the Beckman Institute and the Molecule Maker Labs. You see a picture of it there. Actually, we have 6 or 7, and we use those for different projects. This is a nice collaborative workspace where students from different backgrounds can come together. Students from, material science, from chemical engineering, from chemistry, different backgrounds can come together and think about, prioritizing function, right? How do I get a particular function out? And then also learning some chemistry, along the way. So I would argue then, everything that I just laid out for you, these developments, these recent developments have now enabled us access to very large chemical spaces, right? And there's 2 examples here that I'll just mention even from our own work. And then I'll go into the main story and show you how we use this for light harvesting molecules for organic photovoltaics. And so we've used this method, this automated synthesis method in prior work to synthesize a library of compounds for molecular electronics. Okay, for single molecule electron transport, we basically just had kept the backbone constant. It was a pi conjugated backbone, and we varied the identity of the side chains and asked the question, how does side chain identity affect electron transport? This was an open loop project in the sense that we synthesized and characterized, but we did not use that information. We didn't loop it back to then redesign molecules. And then on the right is a different example, a collaborative project I was involved in where we use closed loop optimization to improve the yields and the general reaction conditions for Suzuki coupling. And we're actually going to use those reaction conditions for the work I'll tell you about today. So, in the work I'll tell you about today, right, we're combining automated synthesis with AI-guided optimization to really focus on a molecular function. Okay, so for a particular example, and the main topic for today, what function do we want to, focus on? So we really decided to focus on, organic light harvesting molecules, but not necessarily just power conversion efficiency to start, but photostability, right? So, okay, think about next generation solar cells. It's very exciting, right? These are transparent, these are lightweight materials. I think there's a lot of opportunities here, right? For future technologies, the power conversion efficiency in recent years has increased to greater than 19% for some of the new molecules. And if we could have advanced manufacturing for high production rates, this could address this 1 gigawatt per day challenge. Very exciting, but there are some challenges. And really, the main challenges, I think, lie in photostability, right? We don't really understand yet how molecular structure controls photostability. That's a complex problem, but we yet need to design molecules that can optimize both, right, efficiency and photostability, right? And in fact, this is such an important problem. It was specifically called out, right, by one of the leading researchers in the field, Lin Lu, who's a professor at Princeton. This is basically a comment article from her group in December of 2020, where they dug into literature and they uncovered 237 papers that had been published in top journals in the last couple of years, all reporting new molecules and new chemistries for OPVs, and only a very small percentage of them even considered photostability. And the ones that did report it, the photostability was not great, right? So it was a comment that we really need to focus on this, but it's a complex problem, right? So photodegradation is complicated because it involves a complex set of physical and chemical processes. Excited state photochemistry is a non-trivial thing to think about modeling, and it depends on the local environment and the chemistry and all sorts of things. So we lack a general set of design principles for controlling that, but I think that this then is a really nice problem, right, for AI-guided closed-loop experiments to sort of use information maybe from prior rounds of synthesis, trying to optimize this objective function. And for us, the objective function will be photostability. So here's a schematic of the process that we developed, okay? And we're calling this closed loop transfer, okay? So as you can imagine, first I've been talking a lot about the fact that we're using a closed loop type method, and that's shown in green, sort of on the left. Indeed, that's true, right? We're using machine learning or, in particular, Bayesian optimization to guide navigation of this large chemical space. We then use automated modular synthesis. We characterize, we loop around here several times to optimize an objective function. But when that's optimized, we then transfer out of this orbit to develop a physics-informed model. And then we use that model to predict into the entire chemical space to see if we can then uncover or discover new molecules. So let me take you step by step. I'll take you through how we did this, and then I'll explain the results and then some next steps. So in phase one, the first phase, this is the closed loop round. Essentially, we're using Bayesian optimization to navigate this really large chemical space. I'll give you some more details as we move forward on all these points. Again, automated synthesis, as I described, to make these donor acceptor oligomers. We experimentally characterize photostability, and we loop around this until we satisfy or optimize an objective function. Once that's done, we transfer out of this orbit, and then we develop models, right? So we do some whole molecule DFT calculations to develop molecular features, and then we develop some physics-informed models based on those features, and this enables us to predict out into the entire chemical space. We can then, maybe the most important thing out of everything here is to experimentally validate the models, right? Because how do we know that anything we actually did was reliable? And so the experimental validation step is quite important. This is used to validate the physical insights that we've gleaned from the models, and really enables learning across a broad chemical space. So, one other comment here. We are talking about, organic light harvesting molecules for OPVs, but in this work, we're really going to focus on just understanding photostability in the solution state. We had to start somewhere. We know that when this goes into a thin film, right, into the solid state, we have to think about film morphology, interfacial effects, and other sort of complicating properties. All those things will be important, but we had to start somewhere, so we started with just photostability in the solution state. So let me go through and kind of, open the hood, and so you can kind of see a bit more of the details in each one of these different phases, how we did it, and then I'll show you the main set of results. So for automated synthesis, we just use a version of the automated synthesis method that I kind of briefly mentioned in the introduction to rapidly prepare these oligomers. But the first question is, what oligomers are we going to make? We had to define, right, the chemical space. And so we decided to choose this donor bridge acceptor motif. Okay, so you can kind of see this here. This is common in organic, electronic organic light harvesting materials. And it's nice because we can readily modularize this scaffold. But the idea is we want to bring in function-infused building blocks in every case, and then prepare those using automated synthesis. So for the donor blocks and the bridge blocks, you can see those there, donor in blue and the bridge kind of in red. These are just inspired by, some successful motifs that we saw in the literature, right? So we had 3 different donors, things like benzodithiaphene, bithiaphene, thiophene. And then for the bridge groups, we have, paralinked phenols, selenophene, things like that. We got more creative with the acceptor blocks. Okay, so shown in green. In theory, any aromatic halide could be used for an acceptor block, right? If you think back to the chemistry, we just need a halide for that last linkage. And so that's a huge space, right? And we don't want to, go through the work of synthesizing these modular building blocks if we don't have to. So we looked into what was commercially available. Well, we asked the students, what are the, commercially available halides from vendors. They identified 5,200 aryl and heteroaryl halides that were, commercially available, reasonable amounts, price less than $150. And so we had to down select, right, from that 5,200 down to 100. We did that just by maximizing chemical diversity, which I can talk about if you want. We have a scheme to do that. It's a quantitative way to sort of maximize chemical diversity, but I apologize for the small font size, right? But the 100 acceptor blocks are kind of shown on the left. That's what we converged on by maximizing diversity. But interesting things popped out, right? Even repurposing, cancer drugs. There's a thyroid cancer drug that we included in the set of 100 acceptor molecules that we used for our synthesis. So in total, we have 3 donors, 7 pi bridges, and 100 acceptors. And if you think about the combinatorics, we get about 2,200 oligomers that can be synthesized. This accounts for symmetry, and for some molecules, we just didn't include a bridge, so it was just donor acceptor molecules. So that's the chemical space, well defined. Okay, what about the synthesis? Okay, I kind of talked about this modular coupling already. We demonstrated that we could do the full two-step synthesis in an automated fashion, right? We only have to do 2 couplings, right, to bring in the pi bridge and bring in the acceptor. We showed that that was possible, but that second reaction is going to be more challenging, right, because we have this really large chemical diversity in the acceptor blocks. So we just decided to make our life easy, and we scaled up, right, the donor bridge coupling step first. We just use a pinnacle ester in the first coupling step, and then we focused on that second step. So it turns out even doing that same chemical reaction, right, even though it's one reaction, it's complicated in terms of yield and optimizing that chemistry because of the large chemical diversity in those 100 acceptors that I already showed. But we tried to standardize it and just use one of 2 general reaction conditions, right? So general reaction condition 1 was from that science paper, the closed loop science paper that I showed you a few slides ago. And if that didn't work, we went to the second general reaction condition. This is more like slow release coupling conditions, which we think really minimizes proto-deboronation, which is a side reaction that can happen. But one of these 2 combined, we got about a 62% success rate for synthesis on the first shot, basically the first choice of acceptor block. And I'll explain to you what happens when we can't achieve that, when we kind of fail on both counts. So that's the synthesis part. We also then, want to think about machine learning or bringing in some AI. And first had to featureize the chemical space. Will facilitate Bayesian optimization to begin with, right? So we featureize this chemical space using different structural and electronic descriptors of all the building blocks. And my colleague Nick Jackson used density functional theory and RDKit. He was able to calculate a large number of electronic structural descriptors for all these different donor, bridge, and acceptor units. Okay, so I'm showing the list here. I won't go through it, but there are some common quantities, or maybe more obvious quantities you might think if we talk about photoactive compounds, so HOMO levels, LUMO levels, things like dipole moments, number of rotatable bonds, things like this. In the closed loop process, we just calculate these for the individual blocks. But we'll revisit that later on in this phase 2, and then we'll do it for the entire compound to see, to make more sophisticated models, essentially. Okay, so we're almost ready to begin, but we want to start round 1. And if we want to use Bayesian optimization, we don't have any prior information in entering round 1, right? Because there are no prior rounds. So we had to initiate this in some way. And so again, we just maximized molecular diversity. We thought that was a good way to do it, prioritize molecular diversity in the entire batch. And that's how we entered round 1. Okay, so this is again kind of showing you the chemical space that we defined. Once the descriptors were calculated, we could look at the maximum variation, basically using principal component analysis, and that's plot as shown on the right. These are both shape and color coded, both for the donor and the bridge blocks, respectively. And so this is basically just showing that we've got a pretty diverse chemical space, right, defined by the chemistries that we've actually selected. So that's featurization. And then in terms of the Bayesian optimization, we're using a technique called Griffin, which was developed specifically, it's a Bayesian optimization technique for chemistry developed by Alana Spiroguzic's group. And essentially, what this will be doing is for every cycle after round one, this algorithm will suggest 6 molecules, and it's basically optimizing photostability. That's the objective function, T80, which I'll define on the next slide. It's a photo bleaching timescale. And it will also be balancing exploitation and exploration in the chemical space. So what does that mean? Well, that means that if we're sitting in a region of chemical space where we're seeing high levels of photostability, we might want to stay there, right, and exploit that region because we're doing really well. But there might be some other global maximum somewhere else, right? And so maybe we should explore a little bit, and so we can balance that kind of in this process. This basically ensures that chemical diversity is prioritized. So here's an example. Let's say we're entering this closed loop round, right? And we're entering round 3, and Bayesian optimizer suggests 6 new molecules. Okay, so there's the PCA plot that I showed you before. The black data points are the molecules we synthesized from the prior 2 rounds, so round 1 and 2, right? And here are the 6 molecules suggested in color for round 3. You can see, they're balancing basically exploration and exploitation with the different colors of the different data points. And in this particular case, this also addresses what happens if we, struck out with those 2 different general reaction chemistries. If we couldn't synthesize a molecule with general chemistry 1 or 2, what the Bayesian optimizer is also doing is suggesting backup molecules, okay? But backup molecules in feature space, not in actual chemical structure space. And then, so in this particular case, we couldn't synthesize molecule C sub 0, right? We just struck out. So we went to C sub 1, we synthesized it, and we moved on, and everything was good for that round. Finally, photophysical characterization. We basically just, characterizing spectral overlap with the solar spectrum. And then also photo bleaching lifetime T80. And then after each round, this information is then fed back to Bayesian optimization again to try, help us navigate this chemical space by maximizing these properties. So after 5 rounds, here's a subset of the molecules that we made. Okay, color-coded, blue, black, and then red, so donor bridge acceptor. And you can see we've got a really, I would say broad chemical diversity. And again, about a 62% synthetic hit rate for that first pass. Interestingly, right, that thyroid cancer drug molecule also was included. It popped out, and we synthesized it, characterized it, and basically as a organic light harvesting molecule. So what about the results? Okay, so we can summarize most of the results on a few slides. So after about 5 rounds of synthesis, okay, in 6 molecules per round, there's 30 oligomers, 30 donor bridge acceptor molecules were synthesized and characterized. And we can plot those results here. So I'm plotting T80, which is this photo bleaching lifetime on the y-axis, and then spectral overlap, on the x-axis. And again, when we started in round 1, we didn't have any prior information. We just maximized, chemical diversity. So we didn't expect those to be particularly photostable, and indeed they weren't. Those are the blue data points. But as we progress from round to round, we want to march along this x is equal to y line. We want to maximize both T80 and also spectral overlap as well, right? And so indeed, by round 5, those are the, I guess, brown colored data points. I'm not sure what color that is, but you can see we're almost forming like this Pareto front, right? And it's almost like we kind of, hit some kind of Pareto front there after round 5. And indeed, another way to look at this data, to plot the progress, is to just think about photostability by multiplying spectral overlap by T80 and then plotting that as a function of the number of molecules synthesized. So the top performing molecule across all rounds is shown. Okay, that actually plateaued after around, round 3 or 4, and then also showing the average of the top 5 molecules. And that seemed to saturate, after rounds 4 and 5, this definition of the objective function, it seemed to saturate. And that's when we decided the campaign was finished. We should probably just finish this closed loop campaign and then move on to sort of model development. Okay, so I would also say, just of note, this to me was remarkable because when we started this project, my intuition was that we would need to synthesize at least a few hundred molecules out of the 2,200 molecules that were possible in order to maximize or optimize an objective function. But indeed, we only had to synthesize about 1.5% of the chemical space. So 30 out of, right, 2,200. And we saturated the objective function in doing so. So, to me, it's just remarkable. So this ends, the first phase, this closed loop round phase, but that's not good enough. We want to develop some physics informed models to see how well we can do some predictions out into the space. And really that's the next step here. We want to develop this physics informed model and ask the question, how can we learn right from the results to gain more predictive power? So we move into phase 2. And so here we did a bit more, Nick's group did a bit more sophisticated simulations, so whole molecule DFT calculations on all the 2200 oligomers. And now they had 114 physical and chemical descriptors, okay? So then we're gonna use those descriptors and to build supervised learning models, basically support vector regression models. Then we're gonna train those to predict out into the space that we didn't explore experimentally, right? So we wanna predict T80 and spectral overlap separately. So here's a summary of the results, right, from the supervised learning and from the predictions. So this is, you're looking at a heat map and basically plotting on the X and the Y axes, all those different features that we were able to sample 114 different features. And we're looking to see which ones predict or, are the most predictive for photostability that we actually measured. So here he explored all possible support vector regression models. And so, 2 descriptor combinations. So it's 114 squared, it's almost 13,000. I can go into the details if you want, but it's the way in which this is calculated. It's technically speaking, you leave out one validation metric to determine R-squared values. I can explain that if you want, but basically the heat map is showing which of these properties are the most predictive. Something that was unexpected to me, for sure, I had expected that just simple T1, so the lowest lying triplet state energies probably would be most predictive of photostability. It turned out that that wasn't true. It was actually the highest energy triplet density of states. So this high energy triplet manifold was the most predictive. And so we'll come back and I'll explain why that happens in a minute, but let's continue with these predictive models. So here's the best 4-feature model that we had, and it was basically trained on triplet density of states then at 2.6, 3.8, 4, and 4.6 electron volts. Again, predicting out into the chemical space, the bottom line again is that if you've got low triplet density of states, then you have higher photostability. You've got longer times to photobleaching, basically, right? So that's the modeling phase, and a lot went into that, but maybe even more importantly is the validation phase, right? So I would say this is the moment of truth, right? This basically assesses the utility of anything that we've done. Is it actually reliable, right? Is it predictable? And we really need to sort of experimentally validate, everything that we've done up to this point, right? So how do we do this? Again, we want to experimentally validate the model. We know that, we've been learning sort of in this low data limit, because we only synthesized 30 molecules. It could induce some false correlations. We therefore want to construct a fair and unbiased experimental test set to see if we can validate these predictions and really ask the question, right, do these high energy triplet density of states, are they really, predicting photostability for these molecules? Because again, that's something that to me was unexpected. So we have to choose a fair validation set. And we want to randomly basically select what we think are the high performers and the low performers. So we take those 2,200 molecules and we just divide them into the top 50 and the bottom 50 predicted performers in terms of the photostability, in terms of the T80 values. And then we just randomly reach in and select 7 from the top, right, and 7 from the bottom, so that we have, to keep things fair, identical spectral overlaps between those two. And then also relatively large standard deviation of the T80 values, which is going to basically just, again, ensure chemical diversity. So that's exactly what we did. Top 50, bottom 50, we reached in, grabbed 7, asked the synthesis team to then make them, right, which took some time. They made them, characterized them chemically, sent them on to the characterization team for photostability, and here are the results. So on the left, you're seeing the predicted top 7 molecules, okay? Interestingly, they're all thiophene-based donors. That's something else that came out of this project, is basically the thiophene-based donors were always more photostable than the benzodiethiophene-based donors, which are shown, basically most of those are the predicted bottom 7 shown on the right, but oddly, benzodiethiophene is more common, I would say, in the literature. Anyway, here are the experimental results in the middle, right, from characterizing photostability. Statistically speaking, we see statistical significance between the predicted, performers in the top 50% and bottom 50%. In fact, well, 6 of the bottom 7 performers that were predicted to be poor are indeed very poor, except one, right? There was an outlier. And this was interesting, and you always learn something, right, from the outlying data. So, just like a human, may not consider all information when making a decision, an AI model may not have all information or didn't know exactly what to look for when you're making predictions. So this is a quinone molecule. It's an anthraquinone. It was the only anthraquinone in the entire 44 molecule set. And what this really suggests is that there's a second mechanism for photostability. It's not only high energy triplet density of states. There's probably something else going on. And we're going to dig into that in a second, but let me just kind of finish the comments about models and validation, and then I'll go in and talk a little bit more about the science. So at the end of the day, we have now 30 plus 14, right? So 44 molecules. We retrained all the molecules on the entire 44 molecule data set, and indeed, high energy triplet density of states even more strongly emerged, right, as critical determinant of molecular photostability. So that increased our confidence. And then if we go back to the 4 feature models and to see how they're predictive, when you incorporate triplet density of states at the high energies at 4 electron volts, you see much more predictive power, right? So this is, again, everything's consistent with everything that we've been, saying so far. So the best performing model at the end of the day, triplet density of states at 2.5 and 3.9 electron volts, also the number of heteroatoms and also the number of rotatable bonds. Okay, so that, to some degree kind of ends, right, the closed loop transfer process. But in the next, 5 or 10 minutes, I didn't answer all the science questions. I want to answer the science questions. Okay, so what are we doing next, though? What can we, do to extend on this? Well, we're trying to predict reaction yields, because if we can increase the reaction yields, we can get to longer molecules, and it increases the efficiency of the entire process. Also, right, then higher reaction yields opens up doors to synthesizing long oligomers and even polymers, something that we're working on at the moment. And of course, moving beyond just solution state, we want to think about film performance and then actually integrating these into OBV devices. My colleague Ying Diao is working on that. Okay, so I talked a lot about predictive models and correlations, but there's, I think, at least three scientific questions that just it wouldn't be satisfying if we didn't answer, right? So first is, first of all, why is that high energy triplet density of states? Why did that emerge as a key determinant of photostability? It was something unexpected for me, for sure. Second is, why was there an outlier molecule, and why was it extremely photostable? And then the third is, can we break out of that plateau, right? That kind of saturation plateau by just redesigning or having a different set of modular building blocks, right? So let's address the first question first. And so we have to go back to some amount of, photophysics and think about a Jablonski diagram, right, for a light absorbing molecule. So let's say, so here we go, right? We have our donor acceptor molecule. Let's say it's sitting in the ground singlet state. It excites incoming light, gets excited to excited singlet state through intersystem crossing, right? It could be converted to a triplet state. It's been disallowed, right? But sometimes it does happen. That state is long-lived and it's highly reactive. And so it could be degraded from there, or it could relax back to the ground singlet excited state. That's typically how we think about fluorophores, at least, for example. However, we also have the solvent around, and I didn't mention, but the solvent that we chose, which is very common in organic photovoltaics or organic electronics, is chlorobenzene. And chlorobenzene is also absorbing the wide, broad spectrum of light that we're putting in, right, from the solar spectrum. We're not putting in monochromatic light in the red, say, for example. We're putting in this broad solar spectrum, so it is also absorbing. And it's possible that it gets excited to its excited singlet. It could be transferred to the T1 state by intersystem crossing. And then, the question is, could that then transfer its energy into the triplet state manifold of the molecule? So to answer that question, we had to go back and ask, again, my colleague Nick Jackson to do some DFT calculations to calculate these relative energies. And indeed, it is possible and quite likely. So the high energy triplet manifold for chlorobenzene is far above that of our donor acceptor molecules. In fact, the T1 energy lies just slightly above the high energy triplet density of states for the donor acceptor molecules that we've considered. So it's very likely that the solvent's absorbing, right? And then it's basically funneling that energy into the high energy triplet density of state manifold, which probably then quickly relaxes down to T1. And that's a highly reactive state for our molecules. And then we see degradation. So if you want to go into the weeds a little bit more, basically this is a triplet-triplet Dexter energy transfer mechanism. It's a 2-electron energy exchange mechanism. I think this is important though for redesigning molecules moving forward. But in any event, right, we consider our donor, it's the solvent, right? It has this excited triplet state in LUMO, and that molecule gets, that electron gets transferred to the acceptor, which is the donor bridge acceptor molecule, and the acceptor then transfers one of its electrons to the donor, and we end up with, right, our donor acceptor in the excited triplet state. This mechanism is relevant and important, I think, and it explains our results because spin multiplicity is transferred during that process. Okay, so that explains, why high energy triplet density of states were important. What about that outlier, right? That's a little bit strange, and it was kind of just hanging out there. So first, why did the AI algorithm, or why did it think it was going to be poor? Why was it predicted to be poor in the first place? Well, it was predicted to be poor because it had a high triplet density of states, at between 3 and 4 electron volts, right? So if it were to only undergo that triplet density of state mechanism that I showed you before, then it would have been a poor performer. But why was it photostable, right? So, I thought back to a lot of the work that we have been doing in my group. My group does a lot of work also in single molecule fluorescence microscopy. And the name of the game there is to increase, photostability. And so try to basically exit your molecules out of any triplet state that they might get into. And so imagine you had a fluorophore, and again, it's undergoing, repeated excitation and relaxation from singlets every now and then by intersystem crossing. It can go into T1. One mechanism or one way to exit it from the T1 state is through a coupled set of reduction oxidation reactions, right? So you can basically exit it through a radical cation and then a radical anion type of coupled redox reaction. That's possible to do. And one of the common reagents that's added at least to aqueous solution is called Trolox. Trolox is a quinone, right? And so it can undergo these reversible redox cycles. And so basically what we think we've had then is a self-healing, OPV molecule. In other words, that acceptor was, internally self-healing because it was a quinone type structure. And if it got itself into a triplet state, it could exit it from that triplet state by undergoing this repeated cycle of reduction oxidation reactions in a reversible manner. And this is just a slide showing that some of the prior work that we've done in my group, we've actually synthesized, this is work we've done a long time ago, dendrimers that actually, these are compact macromolecules with a lot of sort of terminal sites, and we can conjugate different dyes and actually these photo bleaching reagents on, and we improve photostability by doing so. Third question, and the last question, right, is, we hit this kind of plateau in terms of photostability, but maybe, if we had a different set of building blocks, or if we think about putting different function infused building blocks in, we can break out of that plateau. And so that's exactly what we're doing now. So, how do we break out of that plateau, that we observed in the prior round? Let's go back and just redesign some function infused, building blocks. Quinone could be an example of that. Say, for example, that's basically an internal self-healing molecule. But there's other triplet state quenchers that we could put in, right, that don't necessarily need to go through that redox mechanism, right? But there are things like cyclooctatetrene or COT. This is a triplet state quencher that exits molecules by a Dexter transfer mechanism. So it's exactly the other mechanism that we want to basically target. And so my student Sungju is synthesizing building blocks that look exactly like this. He's basically just tethering, right, COT as a triplet state quencher.
We're losing you a bit. Sorry,
okay.
Charles, you were cut off for a minute. If you can please repeat. Sorry about that.
Okay. How far back did I? Just this one slide?
It's just the last phrase. Yeah.
Okay. So the idea is that we can redesign building blocks, function infused building blocks that have different triplet state quenchers directly built into them, right? And so quinone is an example where we could include that specifically, like as an acceptor, as a self-healing type of dye or self-healing type of acceptor unit in an OPV molecule, but that would specifically undergo this redox type mechanism. There are other triplet state quenchers like cyclooctatetrene, shown here, or COT, that are also triplet state quenchers, but exit molecules essentially through a Dexter type mechanism. And so that's exactly the mechanism that we want to target when we think about this high triplet density of states. And so my student Sungju Yi is shown here, and he's synthesizing these function-infused building blocks by specifically linking COT to thiophene, right? And so that's where we are at the moment. We're making them, testing them. I would say the initial result that we have so far, before he went through all the work and synthesized, these custom building blocks, I just asked him to add a bunch of COT to solution with these oligomers to see, and indeed we see this huge increase in photostability, right? There's prior work, one other comment that suggests that even in bulk solid and film, there's one paper that shows that this actually should also work in the solid state as well. So that's really all I wanted to say in 50 minutes or so. So I think it's a successful demonstration of AI-guided closed-loop campaign. We use automated synthesis. We use modular synthesis, which actually enables access to this large chemical space. We successfully navigated this data-scarce regime. We only had to synthesize about 1.5% of the entire chemical space, so 30 out of 2,200 molecules. And this last comment I kind of alluded to, it's interesting, benzodithiophene, which is maybe one of the most popular, I would say, donors, actually showed consistently poor photostability for all of us. Albeit, okay, we're in the solution state, fine, but I think it's important to sort of make a comment about at least photostability. Whereas thiophene donors were consistently more photostable, at least in our hands. These are the students who contributed to the work in my group over the last couple of years. But you saw the acknowledgement slide in the beginning. It really was a team effort. Again, 4 PIs and over 8 graduate students from different groups required to, a several year sort of endeavor to get this to the finish line. So I'm happy to answer any questions from the group. Thank you very much also for the invitation.